We're going to discuss the classical assumptions of the linear OLS model. So most textbooks call these the classical assumptions, but for today we're going to consider these the requirements for a model which follows Gauss-Markov theorem. Now, there are quite a few different ways that we can express these assumptions. Some textbooks take a very mathematical approach and they can surmise the whole thing very quickly just with a system of equations. And many years ago when I was a student, this is what we had to memorize. So number one, the expected value of the error term should be 0. What this means is we expect our additive error term to have a mean value of 0. So the error should be below 0 50% of the time. It should be above 0 50% of the time. The error term is always supposed to be stochastic. It's random. Ergo, we expect it to have a mean value of 0. The second condition is that the variance of the error term is non-finite. In other words, the distribution of your error term should not be purely asymptotic. You should not have infinitely large errors, and you should not have infinitely small or infinitely negative errors. The variance of the error term should be finite. This is what this term on the right-hand side means. It means the variance of the error term is less than infinity. So your error term should have a finite variance. This is required to keep your standard error down. Also, you will probably find your error term should have a finite variance because your x variables, your explanatory variables, ideally would be normally distributed, but there's a caveat to this because we don't really require, indeed we don't actually want, our explanatory variables to have an asymptotic distribution. Quite often our variables do tend to have bounds anyway. For example, if you measure height against weight, well, there's always going to be a lower bound. You can't have negative height, you can't have negative weight. So if you have some sort of logical bound, you're not going to have an asymptotic distribution. The reason why we prefer not to have asymptotic distributions is because this means we can have potentially very large outliers. And when we're sampling against a population, we really do not want large outliers because they can introduce bias into our model. I'll talk about bias in more depth later. I just want to very quickly move across this slide, then we'll talk about the whole thing in words. The third item, the covariance of EI and EJ, so the covariance between the error terms should be 0. So in plain terms here, we're saying we do not want to observe autocorrelation within our model. We don't want the error terms to be affected by the previous value of the error term. We've talked about autocorrelation before, and we'll probably talk about it again today. Number 4, the X matrix is non-stochastic or fixed in repeated samples. This is something we might not have talked about to any great depth. What we mean is when we are taking samples of a population, we do not want the X values to be significantly different from each other every time we take the sample. If the sample is significantly different every time we take it, then we know we are picking up some sort of bias in our sample. So our sample may be overly affected by very large outliers, for example. This is the issue that we have here, and we'll talk about sampling a little bit later. I think through most of what we've done so far, or at least most of what I've done with you, We've talked quite a lot about how we could violate the minimum variance assumptions already. What I don't think we have talked about is the concept of bias. And it's this point number 4, which I think is most likely to introduce bias into our sample. So we do need to be conscious of how we generate bias. And by bias, what I mean is we produce an estimate of beta, which is not equal to the true value of beta. If we have this error in estimating our values of beta, or the values of our slope coefficient, this is what I mean by bias. Last but not least, number 5, the error term should have a normal distribution with mean 0 and a constant variance. So, well, we've already said we expect the error term to have a mean of 0. We do expect it to have a constant variance. If it doesn't, then we have the problem of heteroscedasticity, which we went to very great pains to deal with last week. Last but not least, if you're not familiar with this notation, this n means normal distribution. This 0 is the first moment. This means the mean. This sigma square is the second moment. This is the variance. So what this term here, number 5, means our epsilon t should be normally distributed with a mean of 0 and a variance of sigma square. You'll note here there's no subscript on sigma square. That means that the variance is constant, it doesn't change. If I wrote out sigma square t, this would mean that sigma square depends upon the value of t. So if it was written out like that, we would instantly know we have a heteroscedastic distribution of the error term. We'd know it's non-constant. Okay, so that's a very quick summary of the assumptions. And don't panic, I'll talk about the assumptions and we'll put all this into words. But I want to quickly mention some additional considerations that the textbook doesn't mention, but if you take this for granted, you might be walking up the garden path. Well, first of all, we're going to assume that we have calculated our estimated equation correctly. We're going to assume that our specification is correct. So we've designed a correct regression model that we can safely run. Secondly, we always make an assumption, and this is an assumption that even the textbooks seem to take for granted. What we take for granted.
Hello, Mike, sorry.
Hello.
Do we register this lecture? Is it registered?
What do you mean registered?
Is it recorded? Yeah.
Yes, I'm recording it.
Okay, thank you.
I've forgotten where I was now. What we take for granted is that we have to assume that we have specified the equation correctly and that we've designed a hypothesis which we can test. We also need to be confident that the data that we have collected in order to test our hypothesis is valid data. We need to know that this is well collected. We need to know that this is free from bias. For example, when you're working with macroeconomic data, you need to be sure that all of the variables are collected to the same methodology. So if you're dealing with data, I don't know, let's, for example, consider inflation. If you're dealing with price level data, you need to make sure that the methodology for calculating the price level in whichever country you're dealing with has not changed in that time period. If you have a break-in series, this will be a very significant problem for you. Also, if, for example, if you were dealing with GDP in very recent years, you need to be careful. You might find that some of the values are forecasts. They are not the actual values. Well, a forecast is, shall we say, a best guess based upon what we have already observed. It does not necessarily mean that the forecast is correct. So we need to take things like this into account, that our model is only as good as the data we have. There's that old phrase, garbage in, garbage out. If you put bad data in, you're not going to get a very reliable estimator. That's entirely possible. So you could call this measurement errors. And I think without even looking at the slide, I've actually used the same examples as the slide, which is rather handy. So if we put bad data in that contains measurement errors or is based upon forecast data, we're not guaranteeing that we are going to get a reliable output from the model. So first things first, we need to be confident in what data we're using. So wherever possible, you take your data from reliable secondary sources. In some cases, especially if you're doing microeconomic research, you may have to collect primary data. In the instance where you are collecting primary data, you need to be very careful to ensure you don't ask questions with a biased framing. And you would, of course, have to be very careful that you get a very well randomized sample. So if you're trying, just for example, if you're trying to gauge brand perception on a certain good, you don't do all your questionnaires in the university, because you're going to pick up people of a certain educational background. Most of them are going to live in a similar area. Most of them are going to be a similar age. For example, that would not be a perfectly randomized survey. There's one more point the slide makes, which is rather interesting. Sometimes you can't actually get data for the variable you want, in which case you do this. You use a proxy variable. A proxy variable is something which has the same characteristics as the variable you're actually interested in. But just be aware that proxy variables can be influenced by other factors as well. So this may limit the explanatory power of your model. And if you use proxies, you may find that you put a lot more explanation into your error term here. Okay, so number one, we need to be confident that the data we put in is reasonable, and we need to be aware of any limitations that that data has. The second thing we need to do is follow a logical process as we try and specify our regression model. Now, this is something which you probably haven't had to deal with yet, and the reason we haven't dealt with it is because usually either Shampa or myself will tell you exactly what we want you to regress. In the real world, of course, no one's going to tell you. You've got to design a specification. Now, there are quite a few schools of thought on how you design a specification for a model. Now, what I am going to advise is you follow this method that's suggested on the slide, the parsimonious method. In the parsimonious approach to specifying a regression model, you're going to start with a very large and very general equation. In this initial general equation, you're probably going to add quite a few variables as explanatory. So you're going to put quite a lot of variables on the right-hand side of your equation. So anything that you think could have explanatory effect, you include in the initial model. Then you'll run that model, and you need to make sure that you don't have autocorrelation, you don't have heteroscedasticity, and perhaps most importantly, you need to make sure you don't have multicollinearity. Well, if you do have multicollinearity, then you immediately have to eliminate some variables. Then you need to consider, do I need to put indicator variables in? Would that be more effective? Do I need to consider lagged variables? Do I need to consider using natural logarithms for this model? Once you've done that, so you've eliminated variables that are correlated to each other, you've established the correct functional form for some of your indicators, then you need to start running again, check one more time, no autocorrelation, no heteroscedasticity, no multicollinearity. Then you need to start looking at the t-stats. Once you're confident that you've got nothing which is going to affect your standard errors, you can now trust the t-stats. And you eliminate anything which is not explanatory. So in the parsimonious approach, you're going to start with a very big equation and you start eliminating things from it. It's general to specific. So in this case, the reason we, or at least I would advocate the parsimonious approach, is because it makes it a lot harder for you to omit a variable from your model. And for the past 2 weeks, it's almost become my catchphrase that you can get an impure form of autocorrelation or heteroscedasticity if you omit a variable that has explanatory effect upon the y variable. So you can work around this and minimize your chance of finding heteroscedasticity and minimize your chance of creating autocorrelation by making sure that as much explanatory effect as possible is not in the error term of your model. So this is why I'm very keen on the parsimonious approach. A lot of economists tend to follow this. So general to specific. As you run the parsimonious approach, you need to check that the signs of your coefficients are what you would expect to be finding. You also need to check if there is any existing literature, an existing work which has run a similar regression, that are you matching their findings? That's a helpful check as well. So as you build your econometric model, you need to bear in mind the specification, make sure you are going to get appropriate explanatory power from the model. Try your very hardest not to omit a variable that has explanatory effect. Remember, if you forget to include an explanatory variable, that explanatory power or effect goes into the error term, and that's not ideal for us. So hopefully we now understand the logic of the parsimonious approach. The opposite of this is to start with a specific equation and start to generalize it. This is a lot harder to do. So most people do follow the parsimonious approach. So if you have a hypothesis, you throw every explanatory variable at it and you start eliminating based upon multicollinearity, start eliminating based upon non-significance, and see what that leaves you with. In reality, it's perhaps not common to run a regression with just one variable on the right-hand side. It's possible, but it's not necessarily common. When you start reading academic papers which use econometrics, you very rarely find univariate regression. Okay, so now we've dealt with some things that I would consider just a priors. The reason I think it's important to consider this first is because if you get this wrong, your regression is not going to work. If you specify this correctly, you're sparing yourself an awful lot of trouble. And remember, we found that the vast majority of autocorrelation and the vast majority of heteroscedasticity is actually caused by specification errors. So if you put a lot of effort into specifying the equation, you're more likely to avoid these concepts. Okay, so that's my initial thoughts. Now we can go through a slightly more textbook style approach. Now, I'm just going to follow one book from this point onwards to try and give quite a consistent approach to the lecture. The book I'm following is Studemand, A Practical Guide to Using Econometrics. And these are based upon the slides, which I think Shampa might have briefly shown. Okay, there are, in this version of the classical assumptions, there are 6 core assumptions. However, as you can see on the slide, there are actually 7. The 7th assumption, that the error term is normally distributed, is not a mandatory assumption. However, I would actually like to invoke all 7. The reason being that I want the error term to have a normal distribution wherever possible, because if I do not have a normally distributed error term, then I have issues running my t-tests and my f-tests. So although I don't need a normal distribution for the error term in order to estimate beta, I do require it in order to perform the hypothesis tests. And as you know, the t-test and the f-test are rather vital. So in essence, although number 7 is not mandatory, I do actually need it. So very quickly, and I'll talk about each of these in turn. Number 1, the regression model is linear. Well, we're dealing with the concept of blue OLS here. So one more time. B is best, L is linear, U is unbiased, and E is estimator. Well, best linear unbiased estimator. Well, regression, the first assumption assumes I've got a linear approach. It also assumes that I've correctly specified my equation. So that's what I've just been talking about with picking the correct explanatory variables. And also we have an additive error term. By additive error term, all I mean is we have an error term at the end of the equation. So any variance in y which is not explained by the x variables is explained away by the error term. You need the error term for the equivalence in your regression equation. Number 2, the error term has a 0 population mean. The error term should be stochastically generated. Number 3, all explanatory variables are uncorrelated with the error term. I think we've talked about that a little bit before. There's no causality between them. There's no component of x which correlates with the error term. Number 4, well, we can best express number 4 as saying no autocorrelation. Number 5, we best express as no heteroscedasticity. Number 6, we best express as no strong or even perfect multicollinearity. Perfect multicollinearity is a direct correlation between 2 variables. Usually one is a function of the other. You can have imperfect multicollinearity, which is very strong. That can be a little bit of a problem to us as well. And number 7, we've already discussed. We would like the error term to be normally distributed. The distribution of the error term doesn't really matter in terms of estimating beta. So the blue assumptions focus on how we estimate our betas. However, it's common to invoke the 7th assumption as well, that the error term does have a normal distribution, so it follows a bell-shaped curve. We assume this not because it's important to calculating and estimating beta, we assume this in order that we have hypothesis tests that remain valid. The logic here is that if you relax the seventh assumption, you will get the sign and the size of beta correct. However, you will not be able to determine the significance. Well, given that the standard interpretation is sign, size, significance, in essence, you do need the seventh assumption too. Okay, now I've rushed that, and I know, because the next set of slides talks through each of these in turn. Okay, the first assumption we need to deal with is that we have a linear model, it is correctly specified, and we have an additive error term. So in the example on the slide, it's written out as cross-section because I've got subscript i's. I need to have an additive error term. Et voila, we have one. I will assume that this is correctly specified, and we've already talked about a method for helping us determine what the correct specification is. We've already talked about the parsimonious approach, whereby you start with a very general model, you put in a lot of variables on the right hand side, so you have many x variables, you eliminate anything which is correlated to each other, then you start eliminating what is non-significant. And then you also consider at this point, do you want to use indicator variables? Do we need to use differences or lagged variables if it's time series? Also at this point, you have the option to consider the variance of your specification. At this point, you can also consider the use of natural logarithms. Now, if you want to use logarithms, you need to use the log-log model in order to maintain your compliance with Gauss Markov theorem. So you can either do linear, or you could regress a log-log model. The reason we say log twice is because it means you're going to log both sides. So if you want to use logarithms and you want a regression, you can't just log one side. You have to log both sides. So you'll wind up with ln yi is equal to alpha 0 plus beta 1 x I plus blah blah blah, and plus your error term, but this beta is going to be logged as well. So you log both sides of the regression. Actually, that looks a bit scruffy, so let's write it out again. Sorry, that looked a bit scruffy, so I want to write it out a little bit neater. If you want the log-log model, you have to log both sides of it. That's beta. You should actually write it out like that. That would be the best way to write that out, actually. So you would have to log both sides of the equation. So this is why it's called a log-log model. You can also have lin, log, and log lin. That means one part is a log and one part is linear. In other words, not logged. In reality, you can run log lin and lin log models, but in order to maintain the linearity of your model, you would either need to run both sides as linear on the level. So what that means is you don't log this and you don't log these, or you log both sides of the equation. If you have a multivariate case, it would be normal to consider logging every x variable so far as is appropriate. There are, of course, limitations to this. If you're dealing with growth rates as explanatory variables, you have the possibility to have a negative growth rate, and for a whole host of reasons, you cannot log a negative, in which case you would not be able to log your y variable either if you had growth rates. So here, in order to be correctly specified, we assume we followed the parsimonious approach. We assume we've got a linear structure. By linear, I mean any transformation we make to one side, we must also make to the other side. So if you do want to work with logs, which is quite common, you have to put the logs on both sides of the equation. And of course, you need to now think about how practical it is to log every variable in your equation. So the example I've just given is if you have growth rates, then that's not really going to be possible for you. Okay, so this is quite straightforward. So we need to preserve the linearity here. This is what point 1 deals with. By logging both sides in this case, I've preserved the linearity in the model. Okay, point number 2, the error term has a 0 population mean. Now, what we actually think of the error term as being is stochastic. In other words, it's random. Stochastic means random, just in case you've never heard the word before. When we say something is random, it means we have no predictive ability. It just changes as if on its own. Nothing is able to affect it. Now, the random error term, we assume to have a mean of 0. Now, at this point, I don't have to assume that I have a normally distributed error term, but I do have to assume it has a mean of 0. Now, there's a very handy method I can use here. If my error term does not have an expected value of 0, I can actually work around this. So if my error term, for example, was equal to 5, well, that's a problem because my error term needs to have a 0 population mean. So if the population mean of my error term is 5, I've just violated Gauss Markov, and that's incredibly terrible. However, I can get my error term to equal 0. Well, 5 take away 5 is 0. Can I have my PhD in maths yet? So if I add a constant, the following is going to happen. Usually I just have alpha, but if I have alpha plus 5 plus beta x plus any other beta variable, betas and x's, now I can have eta t minus 5. What happens is if you have an error term which does not have a 0 population mean, this difference is absorbed by your intercept. So your intercept moves up by 5. Now your error term fluctuates about 0. So if I get alpha plus 5, this essentially means my error term has a mean of 0 and whatever distribution is underlying. So where I have a constant term, this helps me correct automatically for any non-zero mean of my error term. So this outweighs that and gives me a mean of 0. Now, this is why it's very common for us to include a constant term in a small sample where you're especially likely to find that the mean of your error term does not equal 0. That difference is absorbed by the constant. It's absorbed by alpha. If you did not include a constant term, if I didn't include the alpha, this minus 5, sorry, this plus 5 here would go onto my beta in that equation. Well, I don't want it to go on my beta. If my estimate of beta plus 5, that may cause me a bias problem. So this is why the constant is very helpful to me. So the regression equation does actually correct for this itself when you run the regression. However, it is better to always run the regression with a constant so that anything goes onto anything is absorbed by the constant term. You just shift the whole constant up by 5, which drops your error term to revolve around 0, rather than have that plus 5 go onto your beta and let the beta variables absorb that plus 5. Remember, the constant is the characteristic that applies through all observations. And it's more important to have a beta, which we can be confident is free of bias, than an alpha. Remember, we don't always interpret the alpha. Sometimes the alpha variable has a very logical interpretation, where x is 0, y equals alpha. Sometimes the interpretation of the alpha variable is not always practical. It's, in fact, not always common sense to try and interpret your alpha variable. So you should find that the distribution of your error term looks a bit like this. Oh dear. I need to turn the pen on. I couldn't find a pre-drawn diagram for this. Okay, let's quickly sketch out the axis. Now let's draw this as a probability distribution. So this is your value of the error term. This is the probability that you get a value of that error term. Now I've got to try and draw something which is vaguely bell-shaped. And as we saw last week, my freehand sketching is not always very good. Right, that's roughly the center point. All right, that's not perfect, but it will do. So you probably should have a mean here of 0. So this is our average e to t. You should find 50% of your errors are distributed below 0. So 50% of your error pulses will be negative. You should find 50% should be positive. Now, I tried to draw it as a bell-shaped curve, but it does not have to be bell-shaped. Here, the average value, however, should be 0. If the average value is not 0, it means the error term has some sort of explanatory effect, and the error term is serving as a constant in the regression. And so if we consider the example we just saw where our error term actually had a mean of 5, if I put another constant into the regression, that cures the problem. And I do not want my error term to have the properties of a constant, because then it has explanatory effect. Okay, so we've dealt with requirement 1, that we have a linear, well-specified model with an additive error term. We've now dealt with why we want our error term to have 0 mean. We don't want it to have the effect of a constant. Secondly, we've hinted at why you probably should include a constant term in your regression. It's not always the case that you will want to interpret the constant alpha. However, if you include the constant alpha, it will prevent any of the constant properties from your error term being absorbed by your beta coefficients. Okay, the third thing we need to deal with is we do not want explanatory variables to be correlated to the error term. Now, I think I introduced that idea last week, when we talked a little bit about homoskedadicity and heteroskedadicity. Look, you can surmise all of that sentence thus, if you prefer the maths, the correlation between an x variable and the error term. If it is equal to 0, then we are following Gauss-Markov theorem. They shouldn't be correlated. If this is not equal to 0, we violate the error term. What this means is there's a component of x, there's some property of x which is related to our error term. In other words, the error term and the x variable as a whole is correlated. And what will happen here is some of the variance of our error term will be captured by our coefficient of x. So when this happens, what you will actually find is the coefficient of x, so that's beta hat, our estimate of beta, is rather likely to increase. Well, if beta increases because our x and our error term are correlated to each other, this means you've added to beta the effect of the error term. Beta should only capture the effect of x upon y. The error term should have nothing to do with it. So here you're going to create bias, and almost always you will create bias upwards. So what you'll do here is you will inflate the value of beta, and in fact it even writes it for you. You will bias the error term, and you bias the error term upwards. Now, let me just clarify what the word bias means in econometric terms. What we mean by bias is that the error term, the beta term, so our estimate, is not that of the true sample. So what we expect in our econometric model is that the expected value of beta hat, so this is what our model produces, should be equal to the real beta value. That's the correct value that we perhaps cannot know. If these are not equal to each other, then our expected beta is either biased below or biased above. So when we say bias, we simply mean the beta estimate is not correct. The beta we calculate is not the true beta. But you can consider the beta as interaction terms between the x variable that beta is the coefficient of and y. If that interaction term is under or overestimated, this biases our model. It either understates the effect of x or overstates the effect of x. This is why we say if the beta we estimate is not the real beta, we have biased our model. So if we have a situation where the error term correlates to a particular x variable, what we will start to see is that variance of the error term which is correlated to x will be captured between the relationship of x and y. So we're likely to pick up a bit more variance of x than we perhaps should have done. Well, if that's the case, then we observe a stronger relationship than we should see. And if this is the case, we have a beta hat, which is probably going to be a little bit higher than the true beta, so we say we're biased upward. This means our model will put too much weight, it'll put too much explanatory effect upon that x which is correlated to the error term. Now, usually we find that if the error term does correlate to one of our x variables, it usually means we've omitted an x variable by accident, in which case, if you do find that there is correlation, you do need to correct for that by re-examining the specification. And once again, the parsimonious approach is our safeguard to help us avoid doing something like this. This is usually a problem which you can cure. In fact, when this problem comes up, you can detect it because you can capture the residuals. If you do detect this problem, of course, number one, you check the specification. The second thing you do is you consider whether logs are appropriate to crush out some of the variance. You might want to use differences or growth rates to see if that has any effect in removing this. If it does not, you will have to you can consider whether X is an appropriate explainer in your model. So there are options to try and work around this. In certain cases, it is possible to overcome this problem. So you should be able to accept assumption number 3 as well. And this comes back to what we've dealt with in the last assumption. We want the error term to be purely random. It should not have any relationship to anything else. Okay, so I think assumption number 3 is pretty straightforward. All explanatory variables should not be correlated with the error term. That's pretty straightforward. Now, what comes next? Number 4, no serial correlation of the error term. Well, serial correlation is also known as auto correlation. They mean the same thing. You can use the terms interchangeably. I think I tend to say auto correlation more commonly. Now, I think we've looked at auto correlation before. We might have done it possibly 2 weeks ago, but I know we have looked at it. In brief, the problem that we find with autocorrelation, and quite like you can typically find, you can find this in time series and in cross section, but it's quite common in macroeconomics at the cross section level. If you are dealing with financial economics and working in time series, you've got a very strong chance that you are going to come up with autocorrelation. Just to sum up, where we have autocorrelation, it means that the previous value of the error term has some sort of explanatory effect upon the current value of the error term. So here, if we write this out, the current error term at ET is explained by ET minus 1 plus an error term. Well, let's put a coefficient here. Let's use the Greek letter rho as our coefficient. Now, if we have no autocorrelation at all, then rho will be equal to 0. That means our error term is only explained by this other error term, in which case our error term is purely stochastic. If, however, we have a rho value which is not 0, it means that the previous error term does have some effect upon the current error term. It means that the error terms are correlated to each other. Now, it's more common here to find positive autocorrelation if you're dealing with macroeconomic data that follows a cycle. So if you've got GDP over 30 years, for example, well, over 30 years, I promise you, you will pick up the economic cycle. The economic cycle, well, the juggler wave, most of the textbooks say the the wavelength is 7 to 11 years. More recently, I tend to disagree with that. The juggler cycle seems to be a lot slower over the last few decades, but still maybe 11 to 15 years. If you have 30 years worth of data, you'll pick up the juggler cycle. What this means is you will start to see a cyclic effect in the data, and therefore the error terms will start to correlate with each other. That's expected where you have a cyclical effect in your data set. So if we have a situation where the error term correlates to each other in large enough sample, you should start to see that the error term will hold a zero mean. However, in smaller samples, if I took GDP over time, but maybe only for 10 years, I might not find that I have a zero error term, in which case I would sincerely hope I have a constant in my regression equation. So I think we've dealt with what autocorrelation is. Before, autocorrelation puts a lot more explanatory effect into the error term, which is something we don't particularly desire. We want the error term to be completely random. And so it is possible that we've omitted an explanatory variable. Once again, we use parsimonious specification to help us avoid this. I don't think we need to go into any more depth on autocorrelation. If you do have autocorrelation, you're probably going to find that in terms of Gauss-Markov theorem, you are no longer minimum variance. So in terms of autocorrelation, you'll find the following. In terms of a blue model, well, you're still going to produce an estimator, you're still linear. You're not likely to find that you're going to unbias yourself with autocorrelation. What you are going to do if you have autocorrelation is that you're not going to be the minimum variance estimator. So you're no longer best in this case. And if you're no longer best, then OLS is probably not the method that you should be using. If you can't overcome autocorrelation, then you would probably be better off using generalized least squares and not ordinary least squares. So you would have violated one of the OLS assumptions. Oh, our old friend has returned, heteroskedadicity. Look, we talked about this in very great depth last week. We assume that the error term should have a constant variance, so the error term should be homoskedastically distributed. If this is not the case, then the error term is heteroskedastically distributed. It means it varies with time. This means that there is some component of our x variables which has a causal effect upon the error term. And so this is paralleling assumption number 3 a little bit, that there should be no correlation with x and the error term. Here in assumption number 5, that we have no heteroskedastic distribution of the error term, we are assuming that x and e are not co-integrated with each other. We don't want to see the error term increasing in its variance as values of x rise, as we want the error term to be constant. And of course, if we have the impure form of heteroskedadicity, then that's caused by an omitted variable, and that's reasonably easy to cure. And once again, we come back to the concept of parsimonious specification and trying to avoid these impure errors. The alternative is that we have the pure form of heteroskedadicity, which is caused by the underlying distribution of a variable. Well, in which case, if we detect this, we might want to consider using logs where appropriate to try and get some of this variance out of our model. Just in very quick summary of the problem before we talk about how we might be able to deal with it. Let's just recap what the problem of heteroscedasticity looks like. Just as a bit of a recap. Okay, so we have, let us assume we have our y variable here, and let's just draw out our x variable here. Now, where we have a heteroscedastic distribution, there is some component of our x variable, there's some factor within it that we called z last week that has an effect upon the error term. Now, when we drew this out last week, we considered a line of best fit, so that's our regression line. We have a constant of alpha, so this line is alpha plus beta x. Then we need to start plotting the distribution of x and y. So let me just change pen color. I think pink might be a nice color. So if we have a distribution which does not, in essence, follow our line of best fit, if the shape around the line of best fit is perhaps a little bit cone shaped, and here we can see that I've got a degree in economics and not a degree in fine art. I really wish I was in US 106 right now because I could draw this on the whiteboard very easily.
Yeah.
Okay, right, I think that's good enough. Hopefully you can see that the pink plots, so these represent individual observations, they form a sort of cone shape. So we go up like that and down like that. So where we have a low value of x, the variance around my line of best fit is quite low. So here, this variance is my error term. So for low values of x, the variance of my error term is quite low. For higher values of x here, my error term has a much greater variance. So here, what we have seen, as this z component seems to increase, we see the variance of our error term increase as well. So what this means is that our error term, it can still be normally distributed, it can still have a mean of 0, but the variance is no longer constant. The variance of my error term is no longer static. Now, this is quite a problem for me. So, okay, we've recapped what a heteroscedastic distribution of the error term might look like. And if you look at a plot of your regression, you can sometimes even eyeball it. And if you're forced to work in Microsoft Excel, this is one of the ways that you can work around not being able to run the white test very easily. Oh, incidentally, you can run the white test in Microsoft Excel. You just have to do it manually, which is rather a drawn-out process, but it is doable. But look, I won't show you how to do that at the moment. It'll take me the best part of an hour to do it. Okay, so let's just change pen color again. In this case, let us consider what's going to happen. Well, I'm still going to produce an estimator so long as my distribution is pretty equal both sides of the line, I'm not going to cause any bias issues, so I'm still unbiased. I'm still going to be linear. That's going to have no effect whatsoever. My problem, once again, is that I'm not going to be best. This means that I'm not going to be able to capture the minimum variance estimator of beta. Here, I would rather expect my standard error to get a little bit larger given this distribution. We ordinarily like our standard errors to be quite low. Here, I'm thinking I have quite a large distribution here. I think there is a component of X which has some sort of explanatory effect. It might be worthwhile to see if I can actually parameterize X and introduce it as a new regressor, which would overcome this problem. If not, I will no longer have a minimum variance estimator. So in this case, there are a couple of options open to me. Number one, I could consider using a log model to see if that has any effect and run the test again. There are some econometric methods which I can use to get estimators of the standard error which are adjusted for heteroscedasticity. There are a few hack methods to do this. That's an option for me too. But for the most part, if this is not caused by an omitted variable, if you can't parameterize this z component of X, then this is caused by the underlying distribution of your X variable. It is somewhat possible. Perhaps a good example here might be that the spending habits of people based upon household income. So if you said X was household income and Y was consumption, you may well find that you do have a distribution that does look a little bit like this. As people have higher household incomes, they have a greater degree of choice in how they spend that income. Some will spend all of the money, some will probably be investing most of the money that they earn. So that may be actually quite a good example of a genuine case where you do have a non-uniform distribution of X, which causes a non-uniform distribution of your error term. For the most part, we do like the X and the Y variable to be normally distributed. Most data should be normally distributed. You're likely to get much more accurate estimations of your beta if we have normally distributed data. However, in some cases, we don't actually want a perfect normal distribution, because a true normal distribution, if you picked up a textbook and started reading about normal distributions, you'd find that a normal distribution is actually asymptotic. In other words, it tends to negative infinity and positive infinity on the x-axis. Now, really, we don't want that in an econometric model, and the reason why is our model is sensitive to outliers, and wherever possible, we do not want extreme outliers, because we are more confident in our estimation of beta if we have a much lower variance in the distributions of X and Y. So perhaps the problem we detect as heteroscedasticity is actually due to the underlying distribution of one of the variables. And if we have quite a wide distribution of one of our X variables, it means it is a lot harder to be confident at, for example, 95%, that we have found the correct value of beta. The wider this distribution, the wider your 95% confidence interval is. The wider that distribution, the greater your standard error is going to be. Okay, so we've dealt with this, and there's another slide which helps us a little bit. Well, we've established that we are still going to be gaining unbiased estimators, but they're no longer blue. Again, the issue is likely to be with our standard errors. Is here where we have an issue with our standard errors, is wherever you see an issue with standard error, you need to start thinking of the t-statistic. Let me give you a quick nudge as to why. The t-statistic in our regressions is equal to the estimated value of beta divided through by the standard error of that estimation. So wherever we have a case where our standard error may not be correct, it may be too big or too small, this will affect our t-stat. Where our standard error is a lot larger, we expect our t-stats to become a lot smaller. Where our standard error is smaller than it should be, our t-stats will be larger. Well, if we have a larger t-stat, that's not too bad for us because it's much easier to accept the alternative hypothesis in the t-test. If you have an inflated standard error, if that's bigger than it should be, your t-stat will be lower than it should be. Well, if your t-stat is lower than it should be, it is harder to reject the null hypothesis. So wherever you see the concept of standard error is just the standard deviation of your estimates of beta, by the way. Where this standard error is not likely to be correct, please immediately think of the t-stat. Someone just mute their microphone. I can hear a car in the background. Okay, so where we have heteroscedasticity, we can't necessarily be certain in which polarity it's going to affect the standard error. So we can't be certain in which polarity it is going to affect our t-stat. So where we have the heteroscedastic distribution, the consequences are going to be this: no longer minimum variance, and the second consequence is because our standard errors are no longer correct, we have no confidence in our t-stat that our regression package will estimate for us. And because we cannot be certain which way our standard errors have been influenced, up or down, it means we do not know which way our t-stat has been influenced. We don't know if it's going to become easier or harder to reject the t-stat. And in this case, if we do not know in which polarity the t-stat is influenced, we cannot be confident in the t-stat. And just a word to the wise, the p-value tests that some of you do are based upon the t-stat. So if you cannot be confident in the t-stat, you're no longer confident in your p-value either. The p-values that you're given in econometric packages are just the probability that you will accept H null. That's calculated for you. It's derived from the t-stat. So you couldn't be confident in either in this case. Also, if you have a non-constant variance of the error term, this can affect the residual sum of squares in the regression. So this means that you would have difficulty being confident in your F-test as well. Oh, and a word to the wiser, if you cannot be confident in the F-test, that unfortunately means you can't be confident in your R-squared either, because the R-square is derived from your F statistic. So the ancillary thing here is we have no confidence in F-stat or in our R-square figures either. Hold on, let me find a blank let's draw a picture to try and illustrate this. Whoops, let me try and get a pen. Will work. I don't really know how this is going to go. Let's get a slightly darker color. Maybe that'll be better for you. Okay, so if we have our estimates of beta hat on the x-axis, now I've got to try and draw a couple of distributions. Now, ordinarily, let us consider a fairly typical distribution. I need these to be as bell-shaped as I can get them. All right, that's not perfect, but it's close enough. Let me just draw another couple of these. I find one that looks like the red. Now let's just do one more to make the example crystal clear. Let's draw a pretty lousy one. All right, that's a terrible distribution in blue, but maybe that's a good thing. Okay, let's get a pen back. Okay, so in each case, these are all the distributions of what value beta can take. Based upon every pair of x and y, they'll form this distribution. And it's the mean of the distribution, it's the dead center point that becomes our beta estimator. Now, as the distribution gets wider and wider, so here standard deviation is increasing and variance is increasing. So in the case of the blue curve, we have a very wide variance that doesn't even look normally distributed. But as we have a much narrower distribution, so in the red case, we have a much lower standard error. It is much more we can be much more confident that we have found the dead center mean. The red curve will be much less affected by extreme outliers. The blue curve will be very greatly affected by extreme outliers. So the more and more that our x values vary, the more and more spread out our standard error of beta is going to become.
Exactly.
And as the standard error becomes more spread out, it's harder for us to be confident that the mean point of this distribution is actually the correct estimator, that it's not biased.
Yes.
So although, because we are assuming that our error term has a zero constant, we can be fairly confident that we don't have the problem of bias here. We're still quite confident that the distribution of our beta is going to be a normal distribution. So in that sense, we're not worrying about the bias, but we now need to worry about the confidence aspect of this. It's much easier to be confident that beta rests in this region than it is that beta rests in this region.
Far distributed.
And so we want the distribution to be quite a bit tighter wherever possible. So in the case of heteroscedasticity, the problem we're going to create is we're going to get a much wider variance
Yeah.
of our possible beta hats. Because these are still going to be symmetrical, I'm not worried about bias, but I am worried about the variance. And ideally, we want the smallest variance possible. So the best curve for me is going to be this red one, because it has a much lower variance. But as our x variable starts to spread out, we're likely to see we move toward the black curve, and if we're having a very bad day, we might even move towards something like the blue curve if we had an incredibly small sample.
Yeah.
Does that clear it up or make it worse?
As the red has a lower variance,
it does.
It has less error term too.
The error term is likely to be a bit narrower. Yes.
Yeah, narrower. Yeah. Okay.
Whereas in the black or even the blue curve, the error term is going to be likely
wider.
Out.
Yeah.
Okay. I think that might have helped, or it might have made it worse, but who knows? Okay.
Yeah.
So I don't know if that helped or not, but oh well, we've done it now. Okay, so we've dealt with heteroscedastic distribution of the error term, and we dealt with this last week as well, and that lecture is definitely recorded on Teams if you really want to see it again. Okay, so we've got two more assumptions that we need to talk about. Assumption number 6 is the last core assumption, and this assumption here is that we have no multicollinearity. If we have perfect collinearity between two variables, as the slide suggests, then you've got two variables that are either exactly the same. Well, that's not likely because you're never going to do that. It's more probable that you'll have variables which are functions or transformations of each other. The slide calls it being a multiple of each other. I would prefer to say that one is a monotonic transformation of the other, or both variables have some constant term within them, which is not very likely. I think the most likely way that we would ever actually pick up perfect collinearity or something close to perfect collinearity would be this second way, that one variable is a multiple of the other or is a linear function of the other. In fact, they don't even need to be linear functions. They can be any monotonic transformation that creates two variables will cause near perfect or even perfect collinearity. Examples of this are not always that easy to come up with. My suggested example here is if we have X1 is equal to the sales revenue of a firm, and let's call it the gross sales revenue of a firm. If I have another variable in the regression, which is the sales tax paid, let's just call it VAT, by that firm, if I put both of those variables in the same regression, I would expect that I would detect multicollinearity between them. That's because sales revenue is 100% of what the firm has received. Let's try and make it neat. The VAT paid, that's VAT that the firm has charged to consumers and will have to pay to the Crown, is likely to be about 20% of their sales revenue. So if my sales revenue increased by just £1,
sales revenue, what do you put in bracket, please?
Just a second. Gross before tax. My VAT that I have to pay would increase by 20p. If my sales revenue were to decrease by £2, then the VAT I pay would decrease by 40 pence, for example. So X2 will always be the same sign. Right? So really, in this case, it's 1/5 of X1 equals X2. So the relationship is always the same here. So any change in X2 is always equal to 1/5 of the change in X1.
Mm-hmm.
So this is an example where I have perfect multicollinearity. I have two variables which are going to share a common path. Now, multicollinearity is probably quite easy to detect. I think 3 weeks ago we detected it just using a correlation matrix. So that's by far the easiest way to do it. In the case of multicollinearity, the problem I have is that if I include two variables which are collinear with each other, I'm going to have two beta terms. So I'm going to have a beta for X1 and I'm going to have a beta for X2. Now, the problem that my regression algorithm, so the problem that Excel or eViews is going to face is how do we attribute the variance in Y given that we've got two X variables which are sharing a common path? Well, in reality, what's going to happen is your OLS regression will not be able to tell the difference between X1 and X2. Your regression equation is not going to be able to attribute variation in Y to X1 or X2 very accurately. Half the variation is probably going to be captured by X1, half the variation might be captured by X2. So in this case, you're not going to generate particularly accurate estimates of your betas if you have perfect multicollinearity, or even something very close to perfect multicollinearity. So, well, the obvious cure to multicollinearity is to not have it. As I mentioned at the very beginning, about an hour and 45 minutes ago, as we follow the parsimonious process of specifying our regression equation, one of the first checks that we should actually make is for multicollinearity. And we should remove variables as appropriate. For example, if I was running a regression to try and determine profit, so if Y in my regression was profit, and I was considering these two X variables which are collinear with each other, I would either have to exclude one or exclude the other. So I might choose to cure the problem just by excluding VAT paid, or I do have another option. The other option is to consider a variable which is an amalgamation of both of them. So I might consider a potential third regressor, which might be net sales revenue. So that's sales revenue less tax. So that combines the characteristics of both X1 and X2 into one variable, which is absolutely fine. So if in this example X1 and X2 were near perfectly correlated with each other, my choice would either be exclude X2 or exclude both of them and include net sales revenue instead. But the easiest way is to avoid multicollinearity. It's usually possible to detect it, and in many cases you can avoid it. In certain cases, underlying variables are very strongly correlated. to each other, you tend to find that consumption and investment have a reasonable correlation with each other, although it's by no means perfect. Getting an example of perfect multicollinearity is much harder to do. You can come close, but to get perfect by accident is near impossible for us to do. So in the case of multicollinear, I think this slide is pretty much saying everything I've just said. In the case of multicollinearity, one variable is a function of another. That if we ignore it, the R square is likely to be rather high. You'll generate a very good measure of the goodness of fit. Such a pity that it's spurious. Once again, we're going to see high standard errors. The reason in this case that you're going to get quite high standard errors is because you won't have a good attribution between x1 and x2 if they're correlated. The regression function is not going to be very efficient in attributing the variance across two betas. Ergo, it's much likely to push your standard errors up. As a result of high standard errors, you're rather likely to get rather low t statistics. And that's a bit of a challenge for you in terms of getting your regression significance. So although your R squared is quite high, your high standard errors are going to make it a little bit harder for you to get your t-stat significant. So if I do have multicollinearity, my R square, and well, if my R square is going to be too high, I would rather suspect that my F statistic is going to be too high as well. If I have high standard errors, my t-stats are going to drop. They're going to drop too low. Well, if my t-stats drop, it's harder for me to be confident in my explanatory variables. Well, if I have high standard errors, you're going to get this point, which I think we've discussed already, that your confidence interval is going to widen. And it has the potential to become rather wide, in which case you are no longer minimum variance. So if I have a very wide confidence interval, the inference is I am not best in my estimator. The last point the slide makes, which perhaps is not too worrying, is that our regression model becomes very sensitive to a change in its specification. If you add in one extra explanatory variable, you will find that the beta values change very significantly for your two multicollinear variables. Well, that should not ordinarily happen. So the consequences here, well, you're still going to have an estimator, you'll still be unbiased. Your estimators won't be reliable, but by the book at least, they won't be unbiased. Yes, you're still going to be linear, that's absolutely fine, but there's no way you're going to be minimum variance because it will be impossible for OLS to maintain its minimum variance approach if you have multicollinearity. Your principal problem is that you will not be minimum variance. It's because Excel or eBuild is really going to struggle to attribute variance in Y to two X variables which are functions of each other. So you're likely to get two estimates for beta that are very spread out. And also, by the book, at least, your variables, sorry, your estimates of beta hat will not be unbiased, but they are rather likely to be inaccurate. But to some degree, you can't guarantee, where you have a small sample size, that is, that you do get accurate estimators. But for most sample sizes, your principal problem is just the issue of minimum variance. And if you have multicollinearity, once again, the solution is to get rid of one of the variables if at all possible. If it's perfect multicollinearity, you have to get rid of one of them or merge them somehow. If it's a weaker form of multicollinearity, it's not strictly a violation of Gauss-Markov, but you might want to consider how you're going to deal with that. That you may find that you can get rid of it, or you may find that you can be confident enough to keep both of them and use a method which is not OLS. As a rule of thumb, generalized least squares is a lot more resilient to this problem than ordinary least squares. Okay. And last but not least, we have our assumptions regarding the error term. I think we've actually mentioned this already. It's not a mandatory assumption to assume that the error term is normally distributed. So here, this is not required for OLS estimation. The seventh assumption is that the error term has a normal distribution. However, I would strongly recommend you do try and invoke this. And the reason why is that although you will get an accurate estimate of beta, it won't be biased, and it won't cause you to lose your minimum variance assumptions. What's going to happen here is that you're going to struggle with your hypothesis tests. So if we do not have a normally distributed error term, that means our t-test would not be reliable, and it means our f-test would not be reliable. So the assumptions required for the t and the f-test do require everything on the right-hand side to be normally distributed. So ergo, we will need a t-test and an f-test. I would generally advise this because you do need to use the t-test and the f-test. You can't avoid it. In all practical senses, this is required in order to assess the stability of your hypothesis and assess the significance of your regressors. Well, ordinarily, we ask you to consider the sign, size, and the significance of every beta that you estimate. Well, you can't estimate the significance if you can't run a t-test. So in reality, you are probably going to assume that the error term is normally distributed. So usually for our error term, we assume a normal distribution, we assume a mean of 0, and we assume a constant variance. And that's one of our equations from the very first slide. So this is the sum of the assumptions that we make about our error term. We do need the normal distribution, which is the bell-shaped curve. We do need a mean of 0, and we do need constant variance. We also saw that we wanted the correlation between our error term and the x variables to be 0. So I also need the correlation between x and my error term to be equal to 0. This means that my error term is independent. It means it's either independent, stochastic, and or random. So this top assumption is my random error term, and this are the parameters of my error term. This describes the type of distribution, the first moment of my distribution, which is the center, should be 0. The second moment of my distribution is the variance. The variance must be constant. So that's the overall characteristic of the error term. Oh, just a word to the wise. If you are interested in confidence intervals, you do need the error term to be normally distributed for your confidence interval as well. Your confidence intervals basically working on the same principles as your t-test. So also your confidence intervals would not be valid if you did not have a normally distributed error term. Okay, That brings us to the end of the 7 core assumptions that we are required to make. Now, believe it or not, I don't actually have much more that I need to run through with you. There are just, I think I've made most of the points that I've got jotted down. There's just a few more things I want to discuss, and perhaps it's better if I just quickly finish, and then we'll have plenty of time to deal with questions at the end. I think I only need about 10-15 minutes maximum to proceed. What I've already mentioned to a fairly decent degree that we need to be rather conscious of the values that we put into our regression. And the issue here is, I want to just mention the sampling aspects of this to you. Now, when you take a population, we have 2 factors that we need to discuss first. The first factor is a population. The second factor we need to consider is a sample. Now, a population is everybody who we can measure to determine a characteristic. The sample is the proportion of the population that we measure. So if we are, let's take a typical regression that we've certainly seen before. Weight is explained by, well, I always want to put a constant in, plus beta 1 height, and well, as we know, I need to have an additive error term. So that should be weight subscript I, subscript I, subscript I. So here's a typical regression. I seem to remember many weeks ago, I think I did actually make you run a regression based on this. Now, it doesn't really matter which way you put weight and height in this regression. It's rather difficult to decide which one causes the other. Well, the population of people who I could measure and survey in order to run this regression is practically every human being in the world. Although if I was just interested in the UK, the entire population of the UK, I could weigh them, I could measure their height. So the population that this estimate would apply to is huge. Now, can I practically weigh everybody in the country and measure everybody in the country?
Impossible.
Well, I can't do it.
Impossible.
So, well, it would take me a very long time, but let's just call it impossible. I agree with you. Well, what if I don't have to do that? I take a sample. So I could possibly just go out with the scales and go out with the measuring tape and take a sample. So instead of measuring and weighing everybody in the UK, what if I just measured and weighed 100 people? So my number of obs could be 100. Well, okay, I can do that, but I need to be very careful. If I accidentally measure a couple of people who are abnormally tall, this is going to skew my sample. So first of all, I need to make sure that I have what is called a perfectly representative sample. Now, what I mean here is that the 100 people I survey reflect in equal proportion the characteristics of the population. So in my sample, I don't want to see a large number of outliers. I want to see most of my observations clustered around the center. Now, in the population, well, if it's the UK population, off the top of my head, it's about 17 million, and I'm just going to sample 100 of them, I need to make sure that my sample reflects the entire population. I need to be sure that I don't give excess weight in my sample to people who are very heavy or very light, very tall or very short. I don't want to capture too many outliers, because outliers are going to start to bias my sample. So the true value, the population, will have this interaction coefficient of beta. My sample, about which I'm going to estimate, is going to have a population coefficient of beta hat. That's my estimate. So if, with my sample, if my value of beta hat that I estimate turns out to be equal to the real value that characterizes the entire population, then I have no bias in my sample, and ergo, so long as I don't do anything else which causes me to violate the assumptions, I can have a blue regression. The problem arises if my sample is not truly representative, then I might put excess weight on my outliers, in which case I create bias and my expected beta would not be equal to the correct value. So the problem I have, oh no, it isn't drawn out, so I will have to draw you a picture to show you what's going on. Okay, this is going to be a hideous diagram, but let's give it a go. We've got time. Okay, so let's have a plane on which I can draw. Pen, I'll keep the black pen for the moment. If I have, now if I'm sampling, it means I probably don't know what the population beta is. But let's say our population follows this distribution. It's close enough to be and it looks like a normal distribution, perhaps a little bit of skewness, but that's not a problem. So here I have my true beta. Now my black diagram is going to be my true population. Now, ideally, what I want to do is this. I want to take a sample. Now, ideally, my sample will have a little bit less variance. I'm going to capture fewer outliers. So my sample might have a beta distribution which looks like this. Well, this is a non-biased sample because the beta equals the true beta. So beta hat is equal to the real beta. So this is a good sample. I may also find a few other characteristics. So let's push our luck and draw a few more. I may find that I get something which looks a bit like this as a sample estimate. Now, this blue one is a skewed sample. In this sample, I've seen some exceptionally low values of beta, but not very many high values of beta. So in this case, my beta hat is below the true value of beta. So this is bias. So that's why when I sample, I need to be cautious of how many outliers I'm picking up. In this blue case, I've obviously picked up a lot of outliers on the left-hand side, but not so many on the right-hand side. That's given me quite a skewed distribution of my sample, and that's dragged my mean point a bit to the left. So that's not good. I've got a biased sample now. The more characteristic case that a lot of the textbooks start to talk about is the whole distribution can shift to the right. or the left. If you're rather like the green case, then you have what's called a shifted sample. If you manage to get a shifted sample where it stands to reason that you have bias, in the shifted sample, it means that the estimate that you have made of your, or the sample you have taken, is completely not representative of the population. So, for example, if you get a shifted sample, what you've probably done is you've surveyed about 100 basketball players instead of surveying the entire representative sample of the UK population. I mean, you can't tell me that a 6'6" basketball player has entirely encapsulates the same characteristics as my granny who's about 5 foot tall. So these are the options that can occur. The black is the true. The red distribution is quite a good sample. That's what I'm looking for. The blue and the green are examples of what can go wrong. Now, this is what bias actually looks like when you start to sketch it out. Your distributions can have a little bit of a skew, but if they are affected quite significantly by outlier values, then this becomes a real problem. So remember that during a regression, what you're actually trying to do is you're probably trying to estimate a population value based upon a sample. Where this is the case, your sample must be reflective. Now, this isn't actually written down in the Gauss-Markov assumptions. However, this is perhaps what I hinted at the start, that you need to use good data. And if you are sampling, you need to make sure your sample is actually a very reflective sample of the population you're trying to estimate a parameter upon. So hopefully that just clears up the sampling concept of beta, that although it's not strictly one of the 7 classical assumptions, if you do not sample correctly, you are able to violate Gauss-Markov. If you don't sample correctly, you will not be unbiased. You will be biased. You can still be best, you can still be linear, but you need to be very careful with the data you put in as well to make sure that you are unbiased. Okay, I think that one rather speaks for itself. Just let me get a print screen of that. Okay, last but not least, properties of the mean. I think we've talked about properties of the mean quite extensively already. In fact, I've shown you that formula. Whoops, I've shown you that formula a few times before. If we have the expected value of beta is equal to the true population beta, then we have an unbiased estimator. I think we've explained that about 3 times now. Remember that your beta hat is the mean of all the possible betas given all of the XY combinations that you can get from your data set. So your beta hat is the average beta value that you could obtain. So this is why we want your data to have a reasonably normal distribution. I don't think there's anything we need to say about this that we haven't said already, because we've discussed bias already. We're doing quite well for time here, which means we can all go to sleep again. Properties of the variance. The last thing I need to mention is, in fact, I have already mentioned this, but just for the sake of repetition, the standard error of your beta is equal to the variance of your beta. I don't know if I wrote that down, so just as a safeguard, let's have a black coloured pen. And what you need to just bear in mind is that the standard error of your beta estimate, so that's what you're given in Excel or in eViews, is also known as the root of the variance of your beta. So in essence, the standard error of your beta, you could also call the standard deviation of your beta. It's the distance of the distribution around the mean, which is of course beta hat. So ideally, we look for standard errors or variances which are quite low. So generally, lower is a little bit better. Now, I think we've already drawn out the diagram of what this is supposed to look like, but there's just one last point which I think is rather helpful. We can manipulate the properties of the variance a little bit, and the rule of thumb is larger samples are better. Now, there are no real laws of econometrics which dictate what your sample size should be. The only thing that really sticks in my mind from my student days is that for every x variable, you should have n equals 10 as a minimum. So if I've got one explanatory variable, I can have 10 observations. If I want 2, I need 20 observations. That's the only thing that really sticks in my mind. But let me show you. Oh, I've just drawn a similar diagram to that. That's rather saddening for me. Okay, let me just add a new slide so I can quickly draw you a diagram to show you what's happening. Okay, I just want to, whoops, didn't want to do that. What I just very quickly want to show you is what the distributions tend to look like as the sample sizes change. So if I draw out the distributions for my beta hat estimates again, for a rather small sample size, you tend to see you don't fully get the bell shape. So you might get something like that. If I have only 5 observations, I get it's like an inverted bowl, I suppose, shape. Quite a large variance here, you see. Well, okay, let's now go on to red. If I now times that by 10, I get something a bit more bell-shaped. The variance is much lower. So here, n might be equal to 50. So as I increase my sample size, what is happening to me is the weight that I apply to outliers, so in this region and in this region, becomes less. Well, these are still technically asymptotic, so I can have large and small outliers, but the relative weight of them drops. Let's do one more just for the sake of it. Now let's perhaps have n equals to, let's times by 10 again, let's have 500. I might get something which looks a little bit more, sorry, that's very sloppy, but I might get something with a much narrower variance as well. So here, the weight of an outlier is much less because I have more observations. Remember, outliers are rare, but outliers have greater effects upon your regression when your sample size is smaller. So in that essence, the variance does matter a little bit. We are seeking to minimize variance. So where we want to minimize variance, it's easier to do it if we have a larger sample size. You start to wear away the effects of the outlier. So if you can regress on the population, you should. If you need to estimate a population parameter, larger sample size tends to be a little bit better. We've talked about the standard error of beta. I've already shown you an equivalent of this diagram. as to what Bayes and samples ought to look like. As a rule of thumb, we've just seen that we can be more confident in our estimators when we have a lower standard error of beta. We usually obtain this, we can try to obtain this with larger sample size wherever possible. And the last point that I just want to reiterate, and I promise it's the last point, is that standard error should always bring up the thought of your t-stat. Your t-statistic is equal to your beta estimate divided through by the standard error of beta. So if you have a larger standard error, it does matter. If you have a lower standard error, it does matter. Well, think of it this way. Let's do a bit of high school maths. Ideally, I want my standard error to be low. Well, if this is lower, my t-stat becomes higher. Well, if my t-stat becomes higher, then I can be more confident in the significance of my finding. I can be more confident in the value of beta, which I have estimated. I can be more confident in this. So standard error does matter. And if at any point you read the term standard error, when you read about OLS, please spare a thought for what will happen to your t-stats. So when you write about the violation of a particular principle of the blue regression, almost all of you in your assessed work did tell me what the effect on the t-stat would be, but think about why this effect occurs. Is the t-stat going to go up or down? Well, if the t-stat goes up, that's probably going to be a good thing, so long as it happens for the right reasons. But if your t-stat goes down, you're going to really struggle to ever accept the alternative hypothesis. You're likely to find that your regression is insignificant. Okay, that's about 2.5 hours. So I think that's quite a nice place to perhaps stop this. Many thanks for watching. I hope you found this useful. This was a live recorded lecture made during the COVID-19 outbreak. The lecture is by no means perfect, but it has been lightly edited to make it available to you online. The bulk of the material is derived from Studemand 2017, and additional material is from Brooks 2013. This was a lecture from our Introduction to Econometrics series at the University of East London's Royal Dutch School of Business and Law.